Okay, so rail grinding is a very important process for the railroads for managing profile quality and rail corrugation and surface damage. And it's one of those expensive and disruptive processes that ideally you wouldn't have to do it, but you do have to manage rail. And if you're going to do it, you may as well do it well, and it's certainly possible to do it poorly. Maintaining rail, you need to manage that process, and so in order to do that, you need to have quality indices in place. With improved technology, we do have the ability to actually monitor and manage each of those different things, the profile quality, the surface quality, and the rail corrugation quality. And so our project is aimed at developing meaningful indices for railroads to manage their grinding program on the basis of those three different parameters.
Thank you, Eric. And now it's Wilhelm.
Simulation of rail milling, comparison to metallography and residual stress measurement. I want to show how important it is that you have to compare your simulations with experiments, because in the future simulations will be more economically to make research and show the people how important is the research on the whole process of maintenance, rolling contact, and something like this.
Thank you. And Matthias, please.
Yeah, multiple squats have multiple causes. What I wanted to point out is that when it comes to multiple squats, it happens where different factors come together. So it's not just the one root cause for multiple squats, it's always a combination of different factors that is mostly leading to multiple squats.
Okay, and Jing.
Okay, the railroad can check condition assessment and maintenance strategy based on the dynamical equivalent chronicity can have the fast calculation and be cost efficient. And today, I have the very impression for the Mr. Aaron Magic's presentation. Maybe we incorporate no method for the profile quality index. So maybe we will develop the real profile index and connect, so for the dynamic equivalent chronicity to maintenance strategy more costly. Thank you.
Thank you. Okay, and now we open for more questions. I think you can continue your question then to Eric, maybe. Okay.
Sure, so I'll finish my question for Wilhelm. So your simulations were based on a new cutting edge, and so the question is, as any given cutting tool reaches the end of its life, the interface between the underside of that tool and the machine surface will start to change, and I just wondered if you could speculate on how that might affect the thermal interaction with the rail and the machine surface.
It will be a part of a future project that we will look at the one cutting edge and the one insert. So now the starting of my PhD project is on a new milling edge, and we compared it to a new, to a process with a tool holder with new milling inserts. So we will make it in the future and have a look on it.
Sounds good. I'll look forward to it.
I have a question for Eric and one for Wilhelm. So I'm quite familiar with block RMS data treatment for corrugation measurements. It works perfectly, and after all, corrugation is not safety critical. Can you comment about the use of a similar indicator for results coming out from non-destructive testing? Because we know that cracks are a local effect, and if you average out over 1 meter or something like that, maybe you underestimate the effect of a single critical defect.
Right. So what we've actually implemented at this stage is we have grabbed the 90th percentile for cracking. So the surface damage index, we're not using an RMS, we're not using an average. We've actually grabbed the 90th percentile. We could grab the 95th, but the idea is that you might have a section of track that's this long and only have one really bad crack. And if you would average, you'd lose it. You wouldn't even know it's there. You wouldn't know that there's one long crack versus a bunch of really, really small cracks. So that's why we are biasing our analysis to take something that's more on, could have gone 99th and 95th. Right now, we plotted the 90th, and we just need to gain more experience to decide what is most sensible for us.
And the question for Wilhelm is about, we know that milling is the only process that is able to remove pretty thick surface from the rail. Why did you perform the job or your research on a 0.9 millimeters depth, while would be interesting to evaluate the possibility of having a single pass 3 mils or something like that, which probably inputs more heat or more energy into the railhead?
The normal process with the standard parameters is 1 millimeter to put away the damaged material. And when you take a second path through it, you see that you have a raise of the temperature in the machined rail, what we will still have remaining on the surface, that is only 320 degrees. And afterward, it will cool down in nanoseconds. So we know that when we have a second path through it, and that there will nothing thermal affect the rail. So it doesn't matter if that you have one path or two paths.
Wolfgang?
Thank you. To go away from the technology free profiling discussion, a more general question to Matthias Luther. I was surprised to hear that 20 years ago the number of squats or rails to be changed because of squats is about the same as today. So in these 20 years we have apparently managed to get rid of hedgex at the gauge corner, and we implemented anti-hedgex profiles and cyclic grinding. So what would you say if I state that maybe the squat problem has been reduced, but the stud problem has come up as a result of too pronounced anti-hedgex profiling, where we may see more in the center of the railhead the defects, and maybe that the target profiles should be reviewed?
Then I say that I'm very sorry that I could not dig into this question, because we had not sufficient information about the profile of our network. This is a question I'm looking forward might be solved in the future by the colleagues from SPB, because I know there's the database to deal with this question. And I'm really looking forward of the results they have with their analysis, how the anti-hedgex profile depends on multiple squat formation.
Thank you.
Because of course your theory is very appealing.
Thank you.
Also one question to Matthias. So we have seen that there are obviously many head-hardened rails in tangent drag. So on the other side there are also many standard carbon in curves. Did you figure out also for the different curve radiuses the differences in the squat occurrence, or was it just above 5,000 meters and below? Because it might be also interesting to see what are the differences between 260 and 350 for the different radius classes below 5,000 meters.
Right now we have only done the analysis for the R350 grade, but we have. I'm not sure if we have the data to do it by radius. I have to look it up. Right now we do not have done this, but maybe this is a good question for future analysis.
So only a quick follow-up for you. So the reason why we chose their 0.9 millimeter, this was a factory track. There were a lot of pits, grooves, some cracks there, so we wanted to create a new rail surface. So that's why we chose that metal removal rate in this specific location, just of the circumstances. So just to clarify this.
This question is for Eric and Wilhelm. We've been addressing the issue of RCF in North America for forever, but I've been in the industry 45 years looking at that RCF. And what my question is to you, Eric, is we have had in the last 20, 30 years or more, a huge amount of effort in North America and other parts of the world for rail profile measurement. So we now have your presentation on these three indices about the corrugation, the cracks, and the profile. And do you have any opinion on how those would be weighted yet, or is there anybody else in your research on that topic about the equivalent index number? Is there anything there that you can comment on that relates to how that might be, because we've had such a huge amount of effort in recent 20, 30 years on profile, not so much on the cracks. So I'm curious to know what that would be in terms of overall real life capability.
So I've always been astonished that the North American freight railroads anyways, they have all sorts of defects, they know where things are, but that generally doesn't come into the rail grinding program. They use the grind quality index for shape, probably because they can put that on the grinder and have access to that. You would think that areas where they have more defects, they would grind more, and areas where they have RCF, problems with ultrasonic tests. A lot of that is just a matter of managing data that hasn't quite made it into the system yet. So there's a heavy reliance on profile, and should there be more consideration of these other things? Certainly, and as they're coming on board, more and more they will. But freight railroads, for example, in North America anyways, don't really have access to that eddy current information. And you'll know that, right? We're involved in some programs with some push push units, but there are systems you can tow behind the vehicles and you can actually get measurements of RCF. But the railroads don't have it yet, so the consideration, the weighting factor on that is 0 at the moment. It's all profile. Should it be greater? Definitely. And as they have the data, I'm sure they will include RCF.
The other part of the question would go to Wilhelm. I think on the milling, we have not had much discussion at all about preventive grinding being confirmed. I think there's a lot of people think that in North America we have preventing grinding, but I don't think that's true because there's not much measurements. It sounds like in Europe, when the work that is done in various places, that it is now mandatory and that it is a given that the milling will for sure remove all the cracks. So my question on that is that ever a part of the discussion in any other work that you do with milling that would make the RCF being completely removed or somewhat completely removed any controversy? Because it sounds like it's just a given and there's a standard and a compliance, and we don't have that in North America. And it sounds like you know, are we missing something about maximizing life cycles by not knowing more about these cracks? The cracks may be the thing that's really killing us. And let's say the profile wasn't perfect, but we get rid of the cracks, what would be the difference, in your opinion, on how we maximize life? Maybe it would be different on heavy axle load, but I'm still curious to know your opinion on this topic in European practice.
That was a question for you.
Oh, really?
Yeah.
Oh, okay, yeah. That was not true. It's your question.
It's my question.
Oh, sorry. Yeah.
No,
Actually,
it's for me.
Wilhelm, sorry, yes, sorry. The milling.
Yes.
The milling.
For me.
Yes, sorry.
I'm not really know because I make only the research part on the simulation and do it for 2 years, and I not really know the track situation in Europe exactly what will happen. You have to ask the company partner.
Maybe Richard?
Maybe Richard.
Because he knows North America too.
Yeah.
Because I think there's some distortion, or we think very different in Europe and North America about certain topics. And this one in particular, I think, is, you know, the law of physics is the same.
So the single cracks in Europe are a general no-go. The single cracks in North America rails are reality.
But I can point to some practical experience on that, because we had a project with the BNSF Railroad where we were trying to get rid of heavy cracking on the rail. And when you have heavy cracking, you get 2 choices often. You might choose to get rid of the cracks and not worry about profile, or you might choose to get to the profile to lower the stress state and then go after the cracks. We were successful on the freight railroad with something we call preventive gradual, which is get to shape first so that the vehicle steers so that you have the contact conditions you've desired, and then progressively chase the cracks. So in that way, I would say the profile is the starting point for that, as long as they're the right profiles. Of course, if you're putting bad profiles on, then you're putting yourself into a high stress state right away.
Okay, I have 2 seconds left. I will put in a very short one. I have a question to the third author. You showed us a pie chart on the effect, just to look into the effects of grinding into the formation of squats. I suppose you made an overall picture for all the rails in your network. Did you try what that graph would look like if you would look specifically for the 350 and the 260 grade?
I can tell you next year. This is what we are doing right now to find out this question.
Okay, thank you.
Okay, so I think we're done then. And thank you being a so active audience. And also we want to thank the technical personnel here for giving us good picture and sound. Yeah.